got nippy all of a sudden. I think you see I had to put on an emergency robe. This is a double Windsor knot, and I much prefer to wear a tie.
'Cause it distracts from my face.
Well, you're looking at the cutting edge of science right there. You see this curve just goes asymptotic to the y aspect. This goes asymptotic to the space aspect. This is the strong force binding two protons together. The middle one is from Wikipedia. The first thing you want to know is the scale. This is the strong force curve. The vertical aspect, force in the fourth power of newtons in decimal. So it's force. The metric of the vertical aspect is force. The metric of the horizontal aspect is linear spatial separation. So that's the entire metric of the space. This is a flat space. It does have a superimposed Cartesian grid. The Cartesian grid here is not being used spatially, except in one dimension. So the horizontal line that's shown as a dotted line, that is the balance of the y aspect. It is where there is no force. So that's what it means in terms of y. There are two ways of looking at it. I'll show you a third. This shows where two protons stop closing distance and go into mutual orbit. You are looking at a limit. In fact, you're looking at the quantum limit. You're seeing a curve through quantum space. This is a quantum of something. The curve is. We're not used to thinking of a curve as anything other than the conjugation of two quantities. You said it correctly. What's the problem? The problem is this curve has its own number system. That is, the curve obeys a number system that is nonlinear. That's what I discovered, is that nonlinear number system. It is, in fact, the conjugation of two linear quantities. You would want to know what the quantities are. Those two curves are perpendicular, and that can be proved in the number space of the curve. This is a force diagram, and so this is a projection downward to flat space, which is how we see, so this is natural to us. You see 3D, but that curve is not passing through linear space, so we can't see it. This curve is equivalent to 1 over x. 1 over x never goes to 0. From that you can prove that x over 1 also never goes to 0. If you stretch your mind to think of 1 as being the identity number, there's the additive identity, which does not affect subtraction or addition. And there's the multiplicative identity number, which does not affect division or multiplication. I discovered what you can say about those two identity numbers. That gives us a direct insight into the meaning of this curve and what it means for the geometry of space. This is not spatial. The curve is nowhere in space, except at one point. We're going to come to find that this makes the point obtain two separate definitions. It depends on what you mean by a point when you say that the curved line intersects the space line. The curved line is a quantity of force, and it's finite at any point. But the problem is the curve has no points. The curve has no points. I proved that. It's continuous or it could not curve. That's the definition of continuity by a geometric definition that can now be proved mathematically. Without the calculus, although we can use the calculus for exactly one operation, and then we never need the calculus again, because we're going to enter calculus solution space. It would be as if you took every calculus book in the world, you just turned back to the solution section and just assume it has all the answers, and just rip out the other 900 pages. So you're left with 100 pages of nothing but solutions. This is the final solution to all the current problems in physics and in mathematics and in human thought. This curve was drawn 270 years ago. This curve shows the relationship between one proton and one proton. Let's take a quick look at the Bošković curve so you'll see what I'm talking about. This is the Bošković Force Curve. It does have the asymptotic curve going up towards vertical infinity, and it does have the asymptotic curve going to spatial infinity. What this means is the force, which is represented by the curve, does not diminish to zero as space approaches infinity. It's asymptotic to spatial infinity. It's a form of parallelity. Mend your mind and heal your mind instantly from what you just dared to try to see by realizing that this vertical asymptote, the curve of force going to maximum force, never achieves maximum force, co-defining spatial infinity and force infinity as never obtaining infinity. Because of something that Bošković discovered, point particle. And that's labeled A. That is a point particle. Is that point the particle or not? This point has to have a radius. It can't just be a point. But by realizing that it has to have a surface, he really saw through the veil. The point particle must be defined in two contradictory ways. He did so and made it work, but he did not quite see into contraspace, which I have seen, and it's mathematically proved on this curve, which, by the way, is a spheric curve. So now I would just like to point out something to you which you've probably noticed already, that if we move this to superimpose on this much simpler graph, in the blue graph is identical with this white graph. Now they're on top of each other, now they're not. That innermost curve from H down to F and then skyrocketing on its asymptote. This multiple curve in the blue area is multiple because it describes the proton-electron relationship. This is the strong force between proton and proton. The one you saw before is proton-electron, but this one is proton-proton. Right away, if you know about electrostatic force, this should be upside down with respect to the other one. Look at it again. What's the relationship? The Coulomb charge relationship, the force relationship between the electron and the proton is that the electron is attracted to the proton. The question is, why does not the electron collide? It can be proved that the electron accelerates toward the proton, and increasingly so at shorter and shorter range. This curve shows that the electron wavers as it accelerates. The question then that you might ask, logically so, does it end up accelerating or decelerating? Does it decelerate as it approaches the proton, or does the electron finally accelerate as it approaches the proton? It should accelerate to infinity. I leave it to you to decide. I won't give away the answer because the ability to see this unlocks the meaning of the force curve. This is the relationship between two forces. Two forces. One of them is repulsive. That's the relationship between two electrons. They repel. A curve can be shown for that that's very simple. They cannot collide. They scatter. An electron cannot be made to collide with an electron. But if they're in close proximity and they have no relative velocity, they will push apart. And even if they're at opposite ends of the universe, it can still be proved that they will still push apart because they have a Coulomb polaric relation of plus or minus on a line. I think you see that that's naive. It's not if you're computing gravity, and this is gravity, of course. An electron exhibits gravity toward a proton. The relationship between the proton is that it is static. It's not moving. It does not move toward the electron, not at all. But the electron moves toward the proton. The proton just sits there with a static force field in space, and the electron navigates it This curve shows how the electron flies toward the proton. This curve shows any number of protons because Bošković figured out the shell system of the harmonic space. That if there are two forces, it's going to attenuate on a certain kind of curve. That's his curve. That's what that is. That is the Bohr atom with electron shells. That's the exact correct curve for the atom. Any atom. You have to find the tipping points where the electrons will stabilize at a certain Lagrangian range. And I incorporated that word, which is taken from astrophysics. The Lagrangian point is one of the points that the James Webb Telescope occupies. There are 5 in a 2-body system. It's at L2, which is technically an Eulerian point, since the 2 stable gravitational points, they're imaginary, but they do exist. Quite a contradiction. Well, you can park a space telescope at a Lagrangian point, and it'll maintain the same relative orientation that you want it to have in order for it to be a stable space telescope in the shadow of the moon, which is a perfect location for that highly sensitive instrument. So, this is the strong force. It has the same double asymptosis profile, without the humps. This is the innermost curve. It is thought of a proton-proton binding action. This asymptote going up gives the exact radius of separation, or you could say diameter of separation, between 2 point particles. That's exactly what Bošković sought to prove, that there must be a distance between 2 particles that cannot be broken. That has been discovered. So Bošković was right. And this is the force curve that proves he was right. This is also the innermost curve of an electron-proton curve. If it were just one electron, this is the curve. If there's one electron heading for one proton, it has to be a simplex hydrogen atom, which most of the universe is made of. That has been fairly well established. So this is a very common element. The way an electron binds with a proton is plotted on this curve, but inverse to the strong force. You would have to turn it upside down. Or you would invert the valence of the metric line, which is force. The space line is constant. It has to be positive. There is a surface of negative numbers that's inescapable in linear algebra. Just as 0 is inescapable, so are negative numbers if you want to exploit the full power of the derivative number system. It's much better to use the universe's number system, which I discovered. This is that number system. It's on the red line. Obviously, it's not linear. But it does have a representation in computers. This curve can be computed to one number, but it's a special kind of number. It's a 4-component conjugal number. I discovered that, and that takes the place of relativistic space that Einstein discovered. I integrated his solution. And that's our introduction to the Bošković Force Curve, which you now see has 3 different representations. A single electron-proton, a multiple protonic center with shells, and the proton-proton binding radius interaction. All of these are quantum units, and they all define light speed. We'll be right back. Thank you for your patience. Keep looking up. I hope you're having a good, jolly, happy season. It's a time of rejoicing. The hot season is over. We're nice and cool now. Stay tuned. We'll be right back.